Okay, so this is lab number 7, binary arithmetic. So here we go with this. So we are going to be making 4 different circuits here. You can just save the very last one, which is the parallel adder. We'll go through parts A, B, C, and D here. So the very first one is the half adder, which looks like this. So I have this already built on my board over here. So it is basically made up of an exclusive OR chip and an AND chip. I labeled these up here. And then I have 2 lights that represent the sum and the carry. And what you're being asked to do is verify the truth table for these. So if we run this over here, I put a little note here. It says the down position of this switch represents a 1. So I'm going to do my A here. So let's look over here. I should be able to get so 0, 0 gave me a 0 and 0. This is 1, 0 I'm giving right now. So that shows me a 1 on my sum, and off on my carry. Changes around, that's both off. See how slow that dims. Let's put that one on. And that's the same deal here. That's a 1. That's a 0. Let's give me a 1 and a 1. Because both of those are down. That's a 1 and a 1. You can see how that now gives me a 0 on my sum and a 1 on my carry. So that is my truth table for this. That is the half adder. So I've verified that table with this circuit here. Okay, that is the half adder. Okay, this is part B of the lab. This is the half subtractor. So you can see the difference here. We now have added the this inverter into the circuit. So A now becomes A naught instead. So let's look at what this results in. So 0, 0. We now have added this inverter in here. So our A signal, the purple wire now jumps over to here and comes back inverted and goes into the AND. Instead, we now call this difference and borrow. So 0 and 0 gives us no lights. Let's turn B to a 1. That gives us both lights. So that is the difference and borrow. Let's flip these around. Wait for them to settle. So that's the 1 and the 0. That gives us a difference, but no borrow. And 1, 1 gives us no difference and no borrow. Alright, that's our truth table for that one. Okay, here we are with the full adder. So in the full adder circuit, we now have a half adder here, another half adder here, and an OR chip here. And then we have our sum light and our carry out light. So let's verify this. This is what it looks like. Some things I messed up when I did this. Make sure you put in this extra wire here. We now have 3 inputs. And then what I did wrong, I was testing this, I had to troubleshoot it. I forgot to add in another resistor up here. 1 resistor for each input we're using, 1 ground wire for each input we're using. There's all my wiring, and let's test this out. So we have 0, 0, 0, has no lights. Carry in only. That one there, that gives us a sum, and no carry. B only is a sum and no carry. B and carry. Is no sum and carry. This thing does take a second for the lights to actually calm down. Let's try A only. Is sum and no carry. Let's try A. Carry. Is carry only. A and B. Is carry only. And then all 3 of them. This is the one that gives us both lights. Okay, so that is our truth table for part C. Okay, this is part D, using the full adder, 4-bit parallel adder. This is the final bit of the lab. So this is what the circuit looks like on the right over here. So basically what we do, we've got 2 banks of dip switches. You can use the red ones or the blue ones, doesn't matter. But basically allows you to fill in a number here and a number here. It's going to add these both together on the parallel adder chip, the 283 chip, and it'll output the results over here on these 5 LEDs, each one representing a bit of a binary number. So our circuit looks like this. So over here, remember that I have used 2 separate dip switches here instead of the 1 bank of dip switches. Remember that we need to put a resistor and a ground wire on each dip switch that we're using. Remember as well, this here, that is the carry out, or sorry, the carry in, or C0 of that chip. That is tied to ground as well. That is this wire right here. That is the carry in, pin number 6. That is tied to ground. Then we should be all set to try some of these combinations. So we say that we are going to try 5 and 5. So 5 is this. That's basically 5 and 0. So 5 and 5 gives me this result here. So that is 0, 1, 0, 1, 0, and that is indeed 10. Let's try 2 and A. That's a 2. A. That's 8. That's 9. That's A right there. So this should be 12. That's 8 and 4 together. That gives us a 12. You can carry on verifying this truth table like that. But basically you should be able to flip your switches, plug in your 2 numbers here, get the proper result here, and basically you've created a little calculator that's capable of adding 2 numbers together. All right, so that is the conclusion of our lab. So fill this all in the multiple choice version that is on Blackboard right now. There's some questions on there to answer as well, and submit that along with saving one of these. Save the parallel adder on TinkerCad. We'll mark your TinkerCad as well. And that is it for submissions for this week. Thank you.